Here comes the sky.
Oscillations are movements that happen over and over again. Could be moving back and forth, up and down, round in a circle. Oscillation, repetitive motion. If we're letting PM stand for periodic motion, which is any motion that repeats itself over and over again, simple harmonic motion will be SHM, which Venn diagram correctly illustrates the relationship between the two. So we know that all simple harmonic motions are periodic motions, and not all periodic motions are simple harmonic motions. That matches up with diagram B. For that same reason, same explanation. Endpoint, equilibrium, and amplitude, you should be able to identify those. Equilibrium point, that's where you have no net force. So the equilibrium, we know there's net force equals 0. It's the place where you're at rest. If you consider the pendulum just hanging down, that hanging down spot when the pendulum is at rest and there's no pushing it or moving it or displacing it or anything like that, the net force equals 0. It's at rest. Maximum velocity happens at your equilibrium. Meanwhile, 0 acceleration is happening because no net force. The amplitude is your distance from your equilibrium, measured in meters usually. Endpoint is the maximum amplitude. So the maximum amplitude is an endpoint. That's where I like to refer everything back to pendulums because they're so nice. You can clearly see the endpoint happens, and that's where the direction is changing, right? So we've gone up, and now we're going back down. And now we've gone up, and now we're going to go back down, and then up and back down. At each endpoint, that is your maximum displacement from the equilibrium. So this is our maximum amplitude. Next, explain what period frequency and angular frequency are. Period is the time it takes or would take for one cycle. One cycle of whatever motion you're dealing with. The frequency is the inverse of your period. It's how often something happens. Period is how long it takes. Frequency is how often it happens. Frequency we usually will measure in hertz. Angular frequency, remember this, 2 pi f. There's our angular frequency. What is a restoring force? I better change colors here. Restoring force points back towards equilibrium. Tries to bring it back home, whatever it is, whether it's a mass on a spring or a pendulum or a physical pendulum, points back towards equilibrium. Fill in the T-table with properties of simple harmonic motion and non-simple harmonic motion. I'm going to fill those in and then I'll unpause to give you the full thing. Hold on. Okay, I had to type it up so you could see it. So for simple harmonic motion, the restoring force is directly proportional to an object's displacement from equilibrium. Meanwhile, for non-simple harmonic motion oscillators, restoring force and displacement have a non-linear relationship. So not only is the relationship linear for simple harmonic motion, it is directly proportional. So that means it's a straight line that passes through the origin. Next, we have all of these versus time graphs: position, velocity, acceleration, force, momentum, kinetic energy, potential energy. They're all of those, if you graph those as a function of time, are sinusoidal. So they're either sine or cosine graphs. Meanwhile, motion, force, and energy graphs do not look like sine graphs for non-simple harmonic motion oscillators. Finally, simple harmonic motion property number 3 is period does not depend on amplitude. That's not how you spell depend, Mr. Scopetus. At least I don't think. Number 3, period depends on amplitude for a non-simple harmonic motion oscillator.